So let's just keep going from where we were before. So last time we looked at Dirac type operators and also symmetric Dirac type operators. So today I want to talk about Dirac bundles. And operators. Okay. So the goal here is that these are really geometrically determined, right? These are purely geometrically determined. Of course, with Dirac type operators, they have a certain condition on their principal symbol that makes them interact in a certain way because they are objects that live on a Riemannian manifold. But here we're gonna look at objects that are even more geometrically determined than those ones. Okay. So let's fix, so Mg for us is a Riemannian manifold. By delta M, we denote the Clifford algebra over the forms. So what is the product with Clifford product? With product eta omega equal to eta wedge omega plus eta cut omega, right? And remember where we recall this cut object is the adjoint. Okay. So now what is a Dirac bundle? So we say that, okay, so I should have maybe said that in the type setting, this is the package backslash slashed. So this is a slashed S. So we have, this is called a Dirac bundle, is a Dirac bundle. So we have a row that takes us from smooth maps into the Clifford algebra to endomorphisms over this bundle. This is an algebra homomorphism. Second point is that this thing, rho EI U, rho EI V, so it's an isometry, right? Okay. And then the third thing is we want it to interact nicely with the connection. So we have that the connection, so it satisfies the product rule. So I'll just slash this actually, just to, it's maybe the cleanest way of writing it, of eta. Yeah, so these are really covectors, right? So maybe I should write uppercase. and I don't know why I wrote it in this way. This is of course just any eta. Right, so for eta in so this satisfies rho. So now this is the Levi-Civita connection acting on yeah. Should be for etas of norm 1. Yes. Eta of norm 1. Yes, that's right. Yes. Okay. Yes, of course. Otherwise, you pick up the norm on the other side. That's true. That's true. It's a one form. Yes. Yeah. Yeah. Okay, and so we have the following product rule. Oops. Just keep writing it as this. And again, this is for eta. That's a one form, right? We only need this for one forms. Okay. So a remark. So this is following Michelson and Lawson, right? So this is following Lawson, Michelson, spin geometry. Actually, it was a bit naughty. I wrote this just out of my memory. I should have really looked at the definition rather than just writing it out of memory. So if there is anything amiss, it would be fixed in the lecture notes. Okay, so the remark. So so the first remark is that by 2, the kernel of rho restricted to one forms is 0, okay, because it's an isometry. And the second point I want to make is that usually, just for shorthand, rho v phi is just written v phi, okay, v dot phi. All right. So now on a Dirac bundle we have a canonical associated operator, which is a Dirac operator. So the Dirac operator. So what is a Dirac operator? So for a point x and EI, an orthonormal frame around x, and the EJ, EI, the coframe, associated coframe. We define Dirac operator. So this is just the sum I equals 1 to n of rho at x ei u at x. So in shorthand notation, of course, this is just now I equals 1 to n ei dot ei u. Of course, this is all evaluated at x. okay, because the representation also depends on X. Okay, so what kind of object is this Dirac operator? So proposition, the principal symbol is just simply psi dot, so it's just simply rho psi. Okay, and D is formally self-adjoint. So the proof of this, well, it's immediately apparent from 2, right? So the proof of this immediate from the second point here, the fact that it's an isometry. Okay. So maybe I'll leave it as an exercise though, because maybe it's instructive to calculate it. But I mean, the point is that because it's an algebra homomorphism, it's going to copy the inverse of an element in the Clifford algebra when its unit norm is just the negative of itself. So one can pull things across in a nice way to get exactly what you want, and the remainder term is of course is a divergence term. So this is why you get that it's formally self-adjoint. So what are the examples? So let S, so the first one I'm going to say is let S equal to just the differential forms, and this is the induced connection from the Levi-Civita connection, from the Levi-Civita then so what we have is this is precisely now equal to eta wedge omega minus eta cut omega, as we wrote before. And so now the point is that D is equal to the Hodge-Dirac, which is just D plus D star with respect to the metric G. And of course the product condition is now also satisfied, right? So if we have a so the bundle now, if we have something product, the bundle also nicely splits. So the second example, a little bit more sophisticated. So let M be spin, and fix a spin structure psi. Let S be the spin bundle with respect to G and the spin structure psi. Okay, so remember the spin bundle depends on both the metric and the spin structure. Then on well, okay, we don't have the time or the energy to get into spin structures. I assume that this is something that people are familiar with. So a spin structure is basically psi is the spin structure, so we fix the spin structure. No, a spin structure determines the spin bundle. Well, it's an object that lives in the cohomology, right? And then from that you construct spin bundles out of a given spin structure. So manifold being spin just means that there are spin structures, but you have to fix a spin structure to talk about a spin bundle. a given spin manifold can have lots of different spin bundles. So okay, so if you want, you can say, okay, fix a spin bundle. So there's a correspondence between spin bundles and spin structures, but of course the bundle construction also relies on the metric G. If you change the metric G, then the spin structure the spin bundle itself might change, because you have to take into account the orthonormal frames, right? So the spin structure descends, so you have a two covering map from spin n to SON, and so all of these things, there's both the geometric data and then there's the topological data that determines the spin bundle. So it doesn't matter, just write, spin structure and the metric, and this can be looked up if you're interested, but the take-home message is that we have something called a vector bundle that is determined by a given spin structure which lives in the topology, and a metric which is the geometric information. Well, I don't know where you've been reading. Typically, if you read Michels and Lawson or Diersinger or whatever, they usually say fix a spin structure psi. I mean, it doesn't matter. It's just, I mean, it's the object that we're calling psi, right? That is, so do you agree that a spin structure can be called a name? It can be called something. It lives somewhere and it can be called something. Well, I want to say that I want to emphasize here that the spin bundle depends on G and psi. So instead of saying that the spin bundle depends on the metric and the spin structure, I'm actually just giving it names. That's all I'm doing here. I'm not going to do any calculations with it. I just wanted to write this sentence G and psi. Okay. Anyway, so then on considering the reducible representations, so everything is complex here. So the canonical I should say the canonical now this toolbar thing is gone again, and I have no idea how to get it back. Oops. Now we've killed it. Now I have to try and find my app again. Oh God. Okay, so I don't know how to do it. I can't find the toolbar.
Are you doing it with your fingers?
No. Alright, so forget that, so I'll have to erase and rewrite. So there is 1 in odd dimensions, 2 in even dimensions. Leads to rho, eta omega equals eta dot omega. Okay. Then this, the induced D is a spin Dirac operator. Okay. And the third example I'll give is building on example number 2. So if we let E be a Hermitian bundle with compatible metric, compatible metric and connection. We can let S tilde slash be the twisted bundle S twisted by E. And this produces, so the reason I wanted to introduce this Dirac bundle language is because Dirac bundles are stable, right? If we take tensor products in this, or if we twist in this way, we still stay in the class of Dirac bundles, right? Produces a new Dirac bundle so we set rho now acting on, so the induced rho is precisely just its action on the first slot twisted by the second. And then the induced operator, so the connection also extends, right? The connection, so we get a canonical connection on S tilde, induced connection, and exercise check this satisfies 1 to 3, this satisfies requirement. Okay, and then the induced, so then we get an induced Dirac operator. So when we have the situation where S tilde is the spin bundle, then this is typically called, then D slash E is typically called the, or twisted Dirac operator. All right. Okay, so now the idea is that so the point of all of this is really to show that there is a very large and non-trivial class of vector bundles and operators that satisfy the hypothesis that we have in the APS theorem, right? So we want self-adjoint adapted operators on the boundary, and we want product type, metrics near the boundary, etc. So all of these things can be satisfied for a very large class on choosing. So I should say in particular for the example 1 and 2. So I'll write that as a remark. Remark for 1 and 2. If G is product near the boundary, then the bundles M and M are product also near the boundary, right? So the point is that this is really, so we get lots of things that are determined purely from the Riemannian metric. Okay, and so we can cook up lots of Riemannian metrics that are nice. I mean, we can take any Riemannian metric on a manifold and deform it in a neighborhood to a product metric, right? So the point is that we have lots of interesting bundles that come out of these considerations. Okay, but now in order to really identify the geometric, so remember in the Atiyah-Patodi-Singer index theorem, so we've seen the eta invariant and we have the index on the other side. But the remaining term that we have is this integral over the zeroth coefficient in the or the constant term or the constant coefficient in the heat kernel expansion. And what we want to do is we want to identify this term, right? We want to geometrically identify this term, because as it stands, it's just an integral that's coming out of a heat kernel. But we want to sort of see this as a geometric object. So for that we need to just digress a little. So genera and forms. Say, well, we can just call it genera. Okay. So so to discuss genera, I just want to get back to the situation. So just a definition. A polynomial map from the matrices which are n by n, complex valued, is said to be invariant if we have that for invertible matrices the following hold, right? Whenever T is in the general linear group, values in C, and X is, of course, well, maybe I'll put C here, and C. Okay, so so this is the notion of an invariant polynomial, and now let's consider a bundle and a connection over M, right? So we're not going to associate a metric here, so this is a complex vector bundle over M, and recall that the curvature, or the curvature of nabla is the following, right? So it's Rxy acting on subsection E is going to be nabla x, nabla y, E minus nabla y, nabla x, E minus nabla xy, lead derivative E. So maybe the choice of, actually let's change the E to a V here, because I'm using E to denote coordinate frames for the tangent bundle, so that's probably not a good idea then to write that. So let Vi now be a frame inside, so I'll call it Ui actually, be a frame inside U. Then the connection 1 form is what? It's nabla x e ui. So of course this is now dependent on the frame. Okay, so this is omega j I x acting on uj. Okay, and also we have a curvature 2 form. The curvature 2 form is, so Rxy ui is now j equals 1 to n of this omega, now j I xy ui. And so the curvature 2 form is this omega ji, where so this is now a 2 form on M, and I should say the connection 1 form. So this is omega ji. This is a 1 form on M. So why is this true? Well, we know that Rxy is equal to negative Ryx, right? So this is the reason that this is a 2 form. Okay. So now the point is, if I define with respect to this basis, okay, so with respect to this local frame, define omega of u to be equal to this matrix. So this is a matrix, it's an n by n matrix, but now it's valued in the two forms. Okay, so this is a two-form valued matrix. Yes. Yes. This is just a bundle. Well, it will be a section, but in particular at each x it's a two form. I'm just writing that to say it's a two form. I mean, it is a section, right? Because but at each x it's going to be a two form. So if you really want, I can. Well, sure. I mean, okay. So this, all right. So this is now u landing us in the one forms. Okay.
Just say use the symbol for the sections and
Yeah. Okay. All right. And okay. So then here we are really looking at u in the two forms as follows. Okay. All right. So it's a two form valued matrix. So actually, one can easily verify that. So it can be verified that the omega ji is what? This is equal to d, the exterior derivative acting on the ji, plus now the sum over say k omega j k omega wedge omega ki. Okay, so this is the so-called curvature 2 form, and this is often how it's defined, right? So just it's really important to emphasize that I'm not writing any coordinate independent expressions here. This is really dependent on the frame. Okay, now let's define, so let the EV of M be the sum of the even form. Okay, so k equals 1 to n of 2k of M. Well, I probably shouldn't be going all the way up to n because, yeah, I mean after some terms it's going to be 0. Okay, so it doesn't really matter. I'll just write k over all n, and then it'll be 0 at some point. Okay, so these are my even forms, and note that EVM with the wedge product is a commutative algebra. Okay, because if we take the wedge of two forms, we get a factor of the minus power of the to the power of the sum of the forms. So if we're in the even algebra, this is always going to be an even number, and so it's the product commutes. Okay, so then any invariant polynomial map P from the matrices NC to C defines P of this now matrix but now it's going to be the even algebra, right? So the point is wherever there's a product, so the polynomial map is going to have some products in there, some scalar products, and that gets replaced by the wedge product in the commutative algebra. Okay, so maybe let's have a look at an example, because this is going to be the most important example for us. So let's suppose that P of x is the determinant of x. So that's equal to what? That's equal to the permutations in Sn of the sign of the permutation, and we're going to just have the scalar product now, I equals 1 to n of x I sigma I. So now what is P of sigma ji, omega ji as a matrix? So this is precisely now where this, it's almost like a functional calculus, right? I mean, you're replacing the product now with the product that appears in the algebra. So this is going to be Sn signum of this permutation, and now I have a wedge product, I equals 1 to n of the sigma I in this way. Okay, so that's just a very concrete example, and that's really the only example that's really the only example that we're going to really need, right? So I could have just started off with this to begin with, but I thought it's just good to have a slightly more broader context to see how all of this stuff fits together. So now I just want to say something. So if ui and ui tilde are two local frames in, say, u, intersect u tilde, then inside u intersect u tilde, we have what? We have, okay, so, well, I won't say that. Then for any invariant polynomial map, P, we have the following. We have that P of omega ij is equal to P of omega tilde ji in the intersection, taking values in the even algebra now. Okay, so so this is very important because, I mean, the point is that the description of the connection forms are local, but this is saying that on the intersections, because of the invariance property of this polynomial map, they give you the same object, right? So the corollary then, so we have P of omega can be defined, so letting omega be the curvature 2 form, so this is of course described locally, right? So I think if you want to describe this globally, you have to really see this in terms of the frame bundle and so on and so forth to make sense of what happens when you have change of frames. We won't get into that. Let's just say, I mean, we understand intuitively what's going on. Locally, I mean, I have a connection, and then I have a connection 2 form associated with this connection, which I can write down locally. So letting this be the connection 2 form, what do we have? So we have that P of omega now is defined on all of M. this is the even algebra. Okay, for any invariant polynomial. Okay. Okay, so how much time do we have? We have 5 minutes, so maybe I can try and say something. So the reason that we want to talk about these things is because we want to also understand certain classes that live in the homology. So let's just recall the following. So recall that we have this following map. We have this so-called cochain complex. So this is just the zero form. So this is just functions. And we have one forms. And we have, okay, so now I can't move this thing because I don't know how to get the, alright, so we have to just write it like this. So we have the n forms, and d squared is of course 0, right? So i.e. this is a cochain complex. So I'm sure many of you are far more experienced and comfortable with this than I am. But this, of course, now allows us to create a cohomology theory, right? So we say psi, well, psi is maybe bad notation because we used it before. So let's say that this is, so recall that this is closed if d psi is 0, and it is exact if this is eta is equal to some d theta. There exists theta. Okay. So with this we get the DRAM cohomology. So let D equal to, so let dk be the map of D restricted to C infinity M to K forms. So this is a map now from K forms to K plus 1 forms. And define this to be the kernel of dk, mod out the image of dk plus 1. Dk minus 1. Okay, so an important theorem now is that for okay, so for P an invariant polynomial, P omega is, well, given a curvature 2 form, given omega a curvature 2 form, P omega is closed, and therefore P omega is an element in the DRAM cohomology, but of order 2k. Okay. But now the point. Okay. So but now the point is that you know. So the remark here is that for an invariant polynomial P, the class P is independent. Well, actually, maybe this should be a part of the theorem still, right? So this is still a part of the theorem. So for an so I should just say then. Sorry, I'll just write the class P is independent of omega. So that sounds really great. It sounds like we're just picking out topological things. However, there is a word of warning, right? So this is true in general, but typically a DRAM cohomology is done on manifolds without boundary, or compact manifolds without boundary. But what happens is that on a manifold with boundary, it may be that P of omega is non-zero, but the class is zero. So the top class, for instance, so the top, say the class of the Hn class might be actually just zero. So it might be something completely trivial at the level of this cohomology, but the P the P omega might still be interesting. So it's saying, so what this is saying for M with boundary, we should care about the form and not just the class. Okay, so that's really just what I want to say.